Tonight, if you were to step outside and look up at a clear sky, far from the glow of cities, it would feel as though the universe is overflowing. Light scattered across the darkness, stars layered upon stars, faint clouds of gas drifting between them, and beyond that, galaxies you cannot see but know must be there. It gives the impression of abundance, of something vast and richly filled. But this impression is deeply misleading. Because when we stop trusting our eyes and begin to measure the universe properly, a very different picture begins to emerge. One that feels quieter, colder, and far more unsettling. On the largest scales, the universe is not full. It is almost entirely empty. Not just a little empty, but overwhelmingly so. If you could somehow remove every galaxy, every star, every planet, every grain of dust, what would remain would look almost identical to what we already have. The vast majority of existence is not made of things, but of nothing. Enormous stretches of space where no light shines, where no structure forms, where even a single atom is a rare event. And yet, this emptiness is not accidental. It is not a temporary gap waiting to be filled. It is not the result of something missing. It is the natural outcome of how the universe is built, and more importantly, how it is evolving. To understand this, we need to begin with scale, because scale is where intuition begins to fail. Imagine shrinking the Earth down to the size of a grain of sand. At that scale, the Sun would be a small, glowing sphere several meters away. The nearest star would not be across a room or even across a city, but thousands of kilometers distant. Entire galaxies would become sparse arrangements of tiny points, separated by distances so large that the idea of structure begins to dissolve. And this is still only a glimpse of the emptiness. Between galaxies, the distances stretch into millions of light years. Regions so vast that light itself takes eons just to cross them. If you were placed in one of these cosmic voids, you could travel at the speed of light for millions of years and still see nothing but darkness in every direction. No stars, no galaxies, no landmarks of any kind. Just silence. These regions are not rare anomalies. They are the dominant feature of the universe. What we call the cosmic web, the vast network of galaxies and clusters, is actually more like a delicate foam. Thin filaments of matter outlining enormous bubbles of emptiness. The structure exists, but it is fragile and sparse, stretched thin across an ocean of nothing. And even within those filaments where galaxies gather, matter itself is surprisingly scarce. Take a single galaxy like our own Milky Way. It contains hundreds of billions of stars, vast clouds of gas, and countless planetary systems. It sounds dense, almost crowded. But if you were to map it out precisely, you would find that the average distance between stars is so large that most of the galaxy is empty space. Even within a star, even within an atom, emptiness dominates. At every level, from the smallest scales to the largest, the same pattern repeats. Structure exists, but it is surrounded, defined, and ultimately overwhelmed by nothingness. So the question becomes unavoidable. Why would a universe capable of forming stars, galaxies, and life itself choose to be built this way? Why is matter so rare? Why is everything so far apart? And perhaps most unsettling of all, why is this emptiness increasing with time? The universe is not static. It is expanding. Every galaxy, every cluster, every distant point of light is moving away from every other. Space itself is stretching, carrying everything with it. And this expansion is not slowing down. It is accelerating. This is one of the most profound discoveries in modern cosmology. Not only is the universe growing larger, but it is doing so at an ever-increasing rate. The distances between galaxies are expanding faster and faster, driven by something we do not fully understand, something we call dark energy. If you could watch the universe over billions of years, you would see galaxies drifting apart, slowly at first, then more rapidly, until entire regions of the cosmos become isolated. Over unimaginable stretches of time, the night sky would grow darker, not because stars are disappearing, but because everything is moving beyond the horizon of what can be seen. Light itself would no longer be able to reach you. And this is not a distant, abstract future. It is already happening. Right now, as you listen to this, galaxies beyond our local group are receding so quickly that their light will eventually never reach us again. They are not just far away. They are being carried beyond the observable universe, slipping out of reach forever. The universe is not just empty. It is becoming more empty with every passing moment. And yet, this raises an even deeper question. If emptiness is increasing, if the universe is being stretched apart, then what is holding anything together at all? Why do galaxies still exist? Why do stars form? Why does structure persist in a universe that seems determined to erase it? The answer lies in a delicate balance of forces, some visible, some hidden, all working together to shape the cosmos in ways that are only now beginning to be understood. Because while ordinary matter, the kind that makes up stars, planets, and everything you can see, is rare, it is not alone. There is something else out there. Something that does not shine, does not emit light, does not interact in ways we can easily detect, and yet outweighs everything we can see by a significant margin. Dark matter. It surrounds galaxies like an invisible scaffold, providing the gravitational pull needed to hold them together. Without it, galaxies would not form as they do. Stars would drift apart. The structures we observe would simply not exist. So even in a universe dominated by emptiness, there are hidden layers, unseen influences shaping what little structure remains. And beyond even that, something more mysterious still. A force that is not pulling things together, but pushing them apart. A force embedded in space itself, driving the expansion of the universe, accelerating it, stretching it beyond anything we once imagined. Dark energy. Together, these two components, dark matter and dark energy, make up almost everything that exists. Ordinary matter, the kind we are familiar with, accounts for only a small fraction of the total. Which means that not only is the universe mostly empty, but what does exist is mostly invisible. And this leads us to a strange and slightly unsettling realization. The part of the universe we understand, the part we can see and touch and measure directly, is the exception, not the rule. We exist in a thin layer of complexity, suspended within a vast and largely unknowable expanse. And yet, despite this, something remarkable has happened. In this quiet, sparse universe, structure has formed. Stars have ignited. Planets have cooled. Life has emerged. Consciousness has developed to the point where it can look outward and ask these questions, all within a cosmos that seems, at first glance, almost completely empty. So perhaps the emptiness is not just a limitation. Perhaps it is a condition, a necessary backdrop that allows everything else to exist. Because if the universe were dense, if matter were packed tightly together everywhere, the delicate processes that lead to stars and planets and life might never unfold in the same way. Gravity would behave differently. Light would travel differently. The balance required for complexity might be lost. In a strange way, the emptiness may be what makes everything else possible. But this is only the beginning of the story. Because to truly understand why the universe is empty, we need to go deeper. We need to explore how it began, how these invisible forces came to dominate, and why this particular moment in cosmic history may be far more temporary and far more fragile than it appears. And as we move forward, the picture will become even more unusual. Because the deeper we look, the more it seems that the universe is not just empty by chance. It may be empty by design. Not in the sense of intention, but in the sense of inevitability. The natural outcome of laws that were set in motion long before the first star ever formed. And those laws are still unfolding. Even now. If emptiness is not an accident, then it must have an origin. To understand where it comes from, we need to move backwards, far beyond galaxies, beyond stars, beyond anything that resembles structure, to a time when the universe itself was something entirely different. A time when everything that now exists, every galaxy, every atom, every particle of light, was compressed into a state so dense and so hot that our usual understanding of space and matter begins to break down. This is where the story of emptiness truly begins. In the earliest moments after the Big Bang, the universe was not empty at all. It was almost the opposite. Energy and particles were packed together in an intense, uniform state, filling space completely. There were no stars, no galaxies, no voids, just a smooth, almost featureless expanse of energy. At first glance, this seems like the opposite of the universe we see today. But within that uniformity, something subtle was already happening. Tiny fluctuations, almost imperceptible variations in density, existed even in those earliest moments. Slight differences, where some regions were fractionally denser than others. These fluctuations were incredibly small, but they would go on to shape everything that followed. Because gravity, even in its weakest form, amplifies differences. Regions that were slightly denser began to attract more matter. Over time, they grew, pulling in surrounding material, becoming the seeds of future structure. Meanwhile, regions that were slightly less dense lost matter, becoming emptier and emptier as the universe expanded. What began as tiny variations would eventually become the vast contrast between galaxies and cosmic voids. But there is another piece of this story, one that is even more important. A moment very early in the universe's history, often referred to as cosmic inflation. For a brief period, lasting only a fraction of a second, the universe expanded at an extraordinary rate. Faster than anything we observe today. Space itself stretched rapidly, smoothing out irregularities, spreading matter apart, and setting the stage for the large-scale structure we now see. During this expansion, those tiny fluctuations were stretched across enormous distances. What were once microscopic differences became macroscopic patterns, embedded into the fabric of the universe itself. The seeds of galaxies, clusters, and voids were laid down in this moment, long before any actual structure had formed. And importantly, this process created vast regions where matter would be scarce. Not because matter was removed, but because space itself had expanded so dramatically that density dropped. Even where matter remained, it became diluted, spread thin across an ever-growing volume. From that point onward, the universe continued to evolve under the influence of gravity and expansion, two forces working in constant tension. Gravity tried to pull matter together, forming stars and galaxies. Expansion worked to pull everything apart, increasing distances, lowering density, and enhancing emptiness. Over billions of years, this balance shaped the cosmic web we see today. Dense nodes where galaxies cluster, connected by filaments of matter, surrounded by enormous voids that contain almost nothing at all. and those voids continued to grow. As matter fell into the denser regions, the emptier regions became even more empty. The contrast increased. The universe did not just maintain its structure, it exaggerated it. It became more defined, more separated, more empty. But this still leaves a deeper question. Why did the universe begin with those tiny fluctuations at all? Why was it not perfectly uniform? Why was there any difference for gravity to amplify? This is where our understanding becomes less certain. Some theories suggest that these fluctuations were the result of quantum effects, tiny, random variations that occur naturally at the smallest scales. During inflation, these quantum fluctuations were stretched into the large-scale patterns we observe today. In this view, the structure of the universe, and therefore its emptiness, is rooted in randomness. Other ideas suggest that the initial conditions of the universe were not entirely random, but there may be deeper laws or principles that determine the exact nature of those fluctuations. But at present, we do not know for certain. What we do know is that once those fluctuations existed, everything that followed became almost inevitable. Gravity would always amplify differences. Expansion would always increase separation. And together, they would always lead to a universe where matter collects into isolated structures, surrounded by vast regions of emptiness. A universe like the one we inhabit. And yet, even with this understanding, there is something about this process that feels counterintuitive. Because we tend to think of the universe as something that should become more complex over time, more filled, more structured. But in reality, the opposite is happening on the largest scales. The universe is becoming more dilute, more spread out, more empty. This is not a temporary phase. It is the long-term direction of cosmic evolution. Stars will continue to form for a time, galaxies will continue to evolve, but eventually, the fuel that drives these processes will run out. Star formation will slow, then stop. Existing stars will burn out. Galaxies will grow dim. And all the while, expansion will continue. Distances will increase. Structures will become more isolated. The observable universe will shrink, not because it is getting smaller, but because less of it remains visible. In the far future, if there are observers still able to look outward, they may see only their own galaxy, surrounded by darkness. The rest of the universe will have receded beyond reach, leaving behind no evidence of its existence. From their perspective, the universe would appear static and alone. A single island in an endless void, which means that we are living in a very particular moment. A moment when the universe is old enough for structure to have formed, but not so old that everything has drifted apart beyond visibility. A moment when we can still observe distant galaxies, measure the expansion of space, and piece together the story of cosmic evolution. This moment will not last forever. In fact, in cosmic terms, it is relatively brief. And this raises a quiet but profound idea, that the emptiness we observe today is not just a feature of the universe, but part of a larger trajectory, a process that began with near uniformity, evolved into structured complexity, and is now moving steadily toward increasing isolation. A kind of unfolding, from dense beginnings to structured middle to an increasingly empty future. And within that unfolding, there is a delicate balance. Because without those early fluctuations, nothing would have formed. Without expansion, everything would have collapsed. Without emptiness, there would be no space for structure to emerge. The universe, in a sense, required both presence and absence, matter and void, structure and emptiness, each one shaping the other. And as we continue to explore this, the picture becomes even more intricate. Because emptiness, as it turns out, is not truly empty at all. Even the void contains something subtle, something difficult to detect, but something that may ultimately hold the key to why the universe behaves the way it does. And to understand that, we need to look closer, not at galaxies or clusters, but at space itself. When we imagine empty space, it is natural to think of it as truly nothing, a perfect absence where no matter exists and no activity takes place. But this idea, while intuitive, turns out to be incomplete. Even in the deepest cosmic voids, where galaxies are absent and particles are incredibly sparse, space itself is not entirely still or inactive. Something remains, something that cannot be seen directly, yet influences the behavior of the entire universe. To understand this, we have to shift from thinking about matter to thinking about the fabric of space itself. In classical physics, space was treated as a passive stage, a backdrop against which events unfolded. Objects moved through it, forces acted within it, but space itself did nothing. It simply existed. Modern physics, however, has revealed that this picture is not quite accurate. Space is not just a container. It has properties, structure, and even energy. At the smallest scales, space is governed by the principles of quantum mechanics. In this framework, what we call empty space is never completely empty. Instead, it is filled with fluctuations, tiny, temporary changes in energy that occur spontaneously. Particles and antiparticles can briefly appear and then vanish again, borrowing energy from the vacuum in a way that is permitted by the rules of quantum physics. These events are incredibly short-lived and difficult to detect, but they are constantly happening everywhere, even in the most seemingly empty regions of the cosmos. This means that the vacuum of space is more like a restless field than a true void. It is active, dynamic, and filled with subtle processes that never fully settle into stillness. And while these fluctuations might seem insignificant on small scales, when considered across the vastness of the universe, they may play a much larger role. One of the most intriguing ideas in modern cosmology is that this underlying energy of empty space could be connected to dark energy, the mysterious force driving the accelerated expansion of the universe. If space itself contains energy, then as the universe expands and more space is created, the total amount of this energy increases. This would lead to a kind of self-reinforcing expansion, where the very act of expanding creates more of the energy that causes expansion. This is one possible explanation for why the universe is not just growing, but accelerating as it does so. It suggests that emptiness is not passive, but active, not just the absence of matter, but a presence in its own right. However, this idea comes with its own challenges. When physicists attempt to calculate the energy of the vacuum using quantum theory, the results do not match what we observe. In fact, they differ by an enormous margin, far larger than can be easily explained. This discrepancy is one of the biggest unsolved problems in physics, sometimes referred to as the vacuum catastrophe. It highlights a gap in our understanding, suggesting that our current theories, while powerful, are still incomplete. So while we can say that empty space is not truly empty, we cannot yet fully explain what it is. And this brings us back to the idea of emptiness on the largest scales. If even the void contains hidden activity, then the distinction between something and nothing becomes less clear. The universe may appear empty in terms of matter, but in terms of energy and underlying structure, it is still deeply complex. This adds another layer to the question of why the universe is the way it is. It is not simply that matter is rare, but that space itself plays an active role in shaping the cosmos. The expansion of the universe, the formation of structure, and the increasing dominance of emptiness are all connected to properties of space that we are only beginning to understand. And as we continue to explore these ideas, a subtle shift begins to occur in how we think about existence. Instead of viewing matter as the primary feature of the universe, with emptiness as the background, we begin to see emptiness as fundamental, with matter as something that emerges within it. A temporary arrangement, a localized concentration, rather than the defining feature of reality. In this view, galaxies, stars, and planets are like patterns that briefly form within a much larger and more persistent emptiness. They are not the default state of the universe, but exceptions to it. Moments of structure in an otherwise diffuse and expanding cosmos. This perspective can feel counterintuitive, even unsettling, because it challenges the way we instinctively understand the world. We tend to focus on what is present, what is visible, what can be touched and measured. But on the largest scales, presence is rare, and absence is the norm. And yet, it is within this rarity that everything we know exists. Which raises a deeper question, one that moves beyond physics and into something more reflective. If the universe is mostly empty, if structure is temporary and increasingly isolated, then what does that say about our place within it? Are we simply a brief anomaly? A fleeting arrangement of matter in an otherwise quiet expanse? Or is there something about this arrangement that is more significant than it appears? From a purely physical perspective, there is no indication that the universe is arranged with any particular purpose. The laws that govern it operate consistently and without direction, leading naturally to the formation of structure in some regions and emptiness in others. There is no preference, no intention, just the unfolding of physical processes over time. But from our perspective, as observers within that structure, the situation feels very different. We experience the universe not as empty, but as rich and detailed. We see stars, planets, landscapes, and other people. Our immediate environment is full of complexity, even though it exists within a much larger context of emptiness. This contrast between local richness and global emptiness is one of the most striking features of the universe. It means that our experience is shaped by a very specific set of conditions, a narrow window in which structure has formed and persisted long enough for us to be here to observe it. Outside of that window, the universe is far less accommodating. And as time continues, that window will slowly begin to close. Because the same processes that created structure are also leading to its gradual decline. Expansion continues to pull everything apart. Dark energy continues to accelerate that expansion, and the overall density of matter continues to decrease. The universe is not moving toward greater concentration, but toward greater dispersion. And this leads us naturally into the question of what comes next. If emptiness is increasing, if structure is becoming more isolated, then what is the long-term fate of the universe? Does this process continue indefinitely, or is there some eventual endpoint, some final state toward which everything is moving? To explore that, we need to follow this trajectory forward, beyond the present moment, into a future where emptiness is no longer just dominant, but almost absolute. One of the clearest ways to see that the universe is not merely sparse, but structured around emptiness, is to look at how galaxies are actually arranged. For a long time, people imagined that if we could zoom far enough out, matter would appear more or less evenly scattered, like grains of dust spread across a dark floor. But when astronomers began mapping the three-dimensional positions of galaxies in detail, that expectation collapsed. Galaxies were not evenly distributed at all. They gathered into clusters, stretched into filaments, formed enormous walls and sheets, and left between them regions so underpopulated that they seemed almost unreal. The universe on its largest scales turned out to resemble a web, with the threads made of galaxies and the spaces between them made of astonishing absence. This is what we now call the cosmic web, and it may be one of the most beautiful and unsettling discoveries in all of cosmology. Within this web, the voids are not minor gaps. They are immense. Some span tens of millions of light years, while others stretch much farther. One of the most famous examples is the Boötes void, discovered when astronomers expected to find an ordinary region of galaxy distribution, and instead found a vast volume with remarkably few galaxies inside it. In a region where thousands might have been expected, only a tiny fraction appeared. It was not absolutely empty, but it was empty enough to force a change in how we pictured the universe. These voids are not errors in the map. They are part of the map. They are not where structure failed to form in some accidental or local way, but where the physics of cosmic evolution naturally drove matter outward into denser boundaries and away from emptier interiors. That process is important because it reveals something subtle about the growth of emptiness. Voids do not simply sit there unchanged while the universe expands around them. They evolve. As gravity pulls matter into denser filaments and clusters, the underdense regions become even more underdense. Matter flows away from them. Their boundaries sharpen. Their interiors become increasingly barren. In that sense, emptiness is not static. It deepens over time. The large-scale universe is a story of separation, with matter collecting into islands, and emptiness claiming more of the space between them. This also means that the structures we admire, galaxy clusters, glowing spiral disks, dense groups of stars, are not the dominant architecture of reality. They are the foam at the edges. The framework is mostly void. If you could stand outside the observable universe and see the whole thing at once, you would not see a packed cosmic city. You would see thin, luminous tracings wrapped around giant cavities. The matter would look secondary, almost delicate, while the emptiness would define the overall shape. And even where matter does gather, another mystery appears. Because galaxies, as we observe them, should not behave as they do if they were made only of ordinary matter. Stars in the outer parts of galaxies orbit too quickly. Galaxy clusters hold together more strongly than visible matter alone can explain. Light bends around massive structures more than it should if only stars, gas, and dust were present. Again and again, observations point toward the same conclusion. There is far more gravitational influence in the universe than visible matter can provide. This is where dark matter enters the story, not as an optional add-on, but as one of the central reasons structure exists at all. Ordinary matter, the small fraction of the cosmos made of atoms, appears to account for only a minor share of the total cosmic energy budget. The rest is dominated by dark matter and dark energy, two components that shape nearly everything on large scales, even though we still do not know their true nature. That is one of the strangest facts in modern science. The visible world feels substantial to us because it is the world we live inside, yet cosmologically, it is the minority case. Most of the universe is not the kind of matter that makes stars or people or planets. Most of it is hidden. Dark matter appears to act as an invisible scaffold. Long before stars formed, it likely began clumping under gravity, creating gravitational wells into which ordinary matter later fell. Gas gathered, cooled, and eventually formed galaxies within these deeper structures. Without that unseen mass, the universe would look very different. The growth of galaxies would be slower, weaker, perhaps insufficient to produce the structures we now observe. In that sense, the visible architecture of the cosmos may depend on something permanently invisible. This gives the universe an almost ghostly quality. The small amount of ordinary matter that shines is like a visible trace of a much larger hidden arrangement. Galaxies are not just suspended in empty space. They are embedded in halos of matter we cannot directly see. Clusters are not simply gatherings of stars. They are concentrations shaped by invisible mass. Even the web itself may be outlined not only by visible galaxies, but by dark matter distributed across enormous scales. And still, even this is not the end of the strangeness, because dark matter helps explain why structures hold together, but it does not explain why the universe is expanding faster over time. For that, cosmologists had to confront an even more surprising discovery. In the late 20th century, two independent research teams used a particular kind of exploding star, type EIA supernova, to measure cosmic distances with exceptional precision. These explosions are useful because they reach nearly the same peak brightness, making them what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears, you can infer how far away it must be. The expectation was straightforward. Since gravity pulls matter together, the expansion of the universe, which began in the Big Bang, should gradually be slowing. The real question seemed to be whether there was enough matter to slow it a little, a lot, or perhaps eventually reverse it. But when those distant supernovae were measured, the results pointed in the opposite direction. They were farther away than expected, implying that the expansion of the universe had not been decelerating as predicted. It had been accelerating. Space was not merely stretching. The rate of that stretching was increasing. That result changed cosmology permanently. It implied that some pervasive influence, now called dark energy, was overwhelming gravity on the largest scales. Gravity still dominates locally, within galaxies, within clusters, within bound systems like our local group. But over great cosmic distances, dark energy wins. It causes space to expand faster and faster, increasing separation and steadily making the universe emptier. The balance has shifted. In the early universe, matter had a stronger role in shaping the large-scale future. In the later universe, dark energy takes over. This is one of the reasons our current era is so peculiar. We live at a time when galaxies still fill the sky, when large-scale structure can still be observed, when the cosmic past is still legible. But that will not last. As accelerated expansion continues, more and more galaxies will slip beyond the cosmic horizon. Their light will never reach us again. Distant clusters will fade from view, not because they stop existing immediately, but because the space between us and them expands too quickly for their future light to cross. The observable universe will become increasingly lonely. Eventually, only gravitationally bound systems will remain together. The Milky Way and Andromeda are expected to merge into a single larger galaxy, and the small local companions bound to them will remain nearby. But beyond that local island, the wider universe will disappear from practical view. Future observers, billions or trillions of years from now, may look into the darkness and find no evidence that the cosmos once contained countless galaxies. They may infer a much smaller universe simply because the rest has become unreachable. That thought is quietly extraordinary. It means that the emptiness of the universe is not just a physical fact, but a barrier to knowledge. Cosmology itself depends on timing. We can understand the universe because we live during a window in which its history is still visible. Too early, and structure would not yet have formed. Too late, and the evidence would be gone. We occupy a narrow interval when the universe is full enough to study, yet old enough to reveal its past. And that does seem worth pausing on, because it changes the emotional texture of the whole story. The emptiness is not just surrounding us in space. It is surrounding us in time as well. We exist in a temporary corridor between a denser past and a far emptier future. Behind us lies an early universe filled with hot radiation and nearly uniform plasma. Ahead lies a universe of increasing darkness, isolation, and thermodynamic exhaustion. The age of stars, galaxies, and visible cosmic history is not permanent. It is a phase. Even now, by the standards of the far future, the universe is comparatively rich. There are still star-forming galaxies. There are still bright young stars, active nebulae, supernova explosions, and giant clouds of gas able to collapse into new suns. In that sense, our universe is not only empty, but also as full as it is ever likely to feel from our perspective, which makes the contrast more striking. If this is one of the fullest eras, and it is already so overwhelmingly sparse, then the future must be emptier in a way that is difficult to emotionally grasp. The next part of that story becomes even colder, because once we look beyond galaxies and expansion and into the deep future of matter itself, emptiness stops being a backdrop and starts becoming the destiny of nearly everything that exists. To follow that trajectory forward, we have to let go of human timescales entirely. The changes we are about to consider do not unfold over years or even millions of years, but over spans so vast that ordinary language begins to feel inadequate. Yet the direction is clear, and it is consistent with everything we have observed so far. The first major transition is already quietly underway. Star formation, the process that gives galaxies their light and structure, is slowing down. In the early universe, galaxies were rich in cold gas, the raw material needed to form new stars. Collisions between galaxies were more common, compressing gas clouds and triggering bursts of star formation. The universe was more active, more dynamic, more productive in a cosmic sense. Today, that activity has begun to fade. Much of the easily accessible gas has already been used. What remains is often too diffuse, too heated, or too gravitationally stable to collapse into new stars efficiently. Galaxies are gradually becoming quieter places. Star formation continues, but at a reduced pace, and over time it will slow further until it effectively stops. When that happens, no new stars will be born. The universe will still contain countless existing stars, but they will simply age and evolve without replacement. Massive stars will live fast and end in dramatic supernova explosions, leaving behind neutron stars or black holes. Smaller stars, like our Sun, will burn more slowly, eventually expanding into red giants before shedding their outer layers and fading into dense remnants known as white dwarfs. And then, after enough time, even those remnants will cool. White dwarfs will radiate away their remaining heat, gradually dimming until they become what are sometimes called black dwarfs, objects so cold and dark that they emit virtually no light at all. Neutron stars, dense and compact, will also cool. Black holes, long thought to be eternal, will slowly lose mass through a process known as Hawking radiation, emitting tiny amounts of energy over extraordinarily long timescales. Given enough time, even black holes will evaporate. This stage of cosmic evolution is often referred to as the degenerate era, a period when the universe is populated primarily by stellar remnants rather than active stars. It is a quieter universe, one where light is rare and most of the energy has already been released. But the process does not stop there. Over even longer timescales, gravitational interactions will slowly dismantle the structures that remain. Stars and remnants within galaxies will occasionally pass close to one another, exchanging energy and altering their trajectories. Some will be ejected entirely, flung out into intergalactic space. Others will spiral inward, perhaps being captured by central black holes before those black holes themselves begin to fade. Galaxies, once stable systems, will gradually lose their coherence. Given enough time, they will dissolve into loose collections of drifting remnants, each moving through an increasingly empty universe with little to anchor them. The cosmic web, once defined by bright filaments and clustered nodes, will become harder to distinguish as its visible components fade and disperse. At this stage, emptiness is no longer just dominant, it is nearly complete. What remains is a sparse scattering of cold, dark objects, separated by vast distances, with very little interaction between them. Energy has been largely spent. Motion continues, but without the same richness of structure or transformation that characterized earlier epochs. And yet, even in this deep future, there is still one more layer to consider: entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. In thermodynamics, systems tend to evolve towards states of higher entropy, where energy is more evenly distributed and less available to do useful work. The universe as a whole appears to follow this principle. Over time, energy spreads out, differences even out, and the ability to drive complex processes diminishes. This leads to what is sometimes called the heat death of the universe. Not an explosion, not a sudden collapse, but a gradual fading into equilibrium. A state where temperature differences are minimal, where no gradients exist to power stars or chemical reactions, where the universe has reached a kind of thermal balance. In such a state, nothing happens in the way we typically understand it. There are no stars forming, no galaxies evolving, no significant sources of light or energy. The universe continues to exist, but it becomes static in a practical sense. Time passes, but without meaningful change. It is a quiet ending. And importantly, it is an ending driven not by destruction, but by dispersal. The universe does not run out of space or collapse in on itself in this scenario. Instead, everything spreads out. Energy becomes diluted. Matter becomes isolated. Emptiness becomes the defining condition. From this perspective, the emptiness we observe today is not just a feature of the present, but a preview of the future, a glimpse of what the universe is becoming. And yet, there is something subtle in this progression that is easy to overlook. The very processes that lead to this eventual emptiness are the same processes that made everything possible in the first place. The expansion of the universe allowed matter to cool and form structures. The imbalance of energy enabled stars to ignite. The flow of time, driven by increasing entropy, created the conditions under which complexity could emerge. Without these processes, there would be no galaxies, no stars, no planets, no observers. The path toward emptiness is also the path that allowed existence as we know it. This creates a kind of symmetry. The universe begins in a hot, dense, highly ordered state, evolves into a structured and dynamic middle phase, and moves toward a cold, diffuse, high-entropy future. Each stage is connected. Each follows naturally from the one before. And within that arc, we occupy a very particular position. We exist in the era where the universe is still active, still forming stars, still rich enough in structure to support life and observation. We are far from the dense beginnings, but also far from the empty end. We are in between, in a phase where complexity is possible. That positioning is not necessarily special in a broader sense, but it is significant for us. It determines what we can observe, what questions we can ask, and what answers we are capable of finding. Because if we existed much later, the universe would look very different. There would be no distant galaxies to study, no clear evidence of cosmic expansion, no visible trace of the Big Bang. The sky would be darker, simpler, and far less informative. Entire fields of science might never develop, simply because the data would no longer be accessible. In that sense, emptiness is not just a physical reality, but a limit on knowledge. The more empty the universe becomes, the less there is to observe, and the harder it becomes to reconstruct the past. Information is not destroyed immediately, but it becomes increasingly difficult to access as light fails to reach observers and structures disperse. So the universe is not only becoming more empty, it is becoming more opaque to understanding. And yet, even this is not the full story. Because while the overall direction points toward increasing emptiness, there remain open questions about whether this path continues indefinitely, or whether something unexpected could alter it. Some theories suggest that dark energy may not be constant, that its strength could change over time. If it were to increase, the expansion of the universe could become even more dramatic, potentially leading to a scenario sometimes called the Big Rip, where galaxies, stars, and eventually even atoms are pulled apart by the expansion of space itself. Other possibilities suggest that new physics could emerge at extreme scales, altering the long-term fate of the universe in ways we cannot yet predict. At present, the evidence points toward a future of continued expansion and increasing emptiness. But our understanding is not complete. There is still room for surprise. Even so, the general picture remains consistent. The universe began dense, became structured, and is moving toward emptiness. And in that movement, there is a kind of quiet coherence. Not a purpose, not a direction in the human sense, but a pattern that unfolds according to the laws of physics, shaping everything from the largest cosmic voids to the smallest quantum fluctuations. And perhaps the most striking part of this entire story is not just that the universe is empty, but that within that emptiness, something like us was able to emerge, to observe, and to understand. Which brings us, finally, to the question of what that emptiness really means. When we return, after all of this, to the idea of emptiness, it no longer feels like a simple absence. It is not just empty space between objects, not just distance, not just darkness. It is something far more fundamental. It is the dominant state of the universe, the condition into which everything expands, the backdrop that both allows structure to form and ultimately dissolves it. And yet, from where we stand, it does not feel that way. Our experience is local. We live on a planet, orbiting a star, within a galaxy that contains hundreds of billions of other stars. Around us is complexity, motion, light, and change. Even when we look up at the night sky, what we see is not emptiness, but points of brightness scattered across the dark. It feels populated, almost crowded, despite everything we now understand about scale. This contrast is important because it highlights a kind of perspective illusion. On small scales, the universe is dense enough to feel full. On large scales, it is overwhelmingly empty. Both of these statements are true at the same time, but they belong to very different frames of reference. What feels like abundance to us is, in a wider context, a rare concentration. It is a little like standing in a forest and assuming the entire world is filled with trees, when in reality, the forest is just one small region within a vast, open landscape. Our position shapes our perception. And in that sense, emptiness is not something we directly experience. It is something we infer. We calculate distances, map distributions, measure radiation, and build models that reveal the larger structure. Without those tools, the universe would seem far more full than it truly is. This raises an interesting point about understanding itself. Much of what we know about the universe comes not from direct experience, but from interpretation. We take limited observations and extend them outward, guided by physical laws that appear consistent across space and time. We trust that the same principles apply in regions we cannot reach, in epochs we cannot witness. So when we say the universe is mostly empty, we are not describing something we have fully explored, but something we have reasoned out. And that reasoning so far has been remarkably successful. It has allowed us to predict the existence of cosmic microwave background radiation, to map the distribution of galaxies, to infer the presence of dark matter, and to detect the accelerated expansion of space. Each of these discoveries has reinforced the same underlying picture: a universe where matter is sparse, where structure is isolated, and where emptiness dominates. But there is still something slightly counterintuitive about calling this emptiness nothing. Because, as we have seen, it is not truly nothing. Space has properties. It has energy. It can expand, stretch, and influence the motion of matter. Even the vacuum is active, filled with fluctuations that hint at deeper layers of reality. So perhaps a more accurate way to think about emptiness is not as the absence of everything, but as the absence of the things we are familiar with. No stars, no planets, no visible matter, but still something. This shift in perspective makes the universe feel less like a place where things exist within nothing, and more like a place where familiar structures emerge within a broader, less tangible foundation. Matter becomes the exception. Emptiness becomes the rule. And yet, despite being the rule, emptiness does not feel dominant in our daily lives. We are surrounded by matter, by solid objects, by interactions that feel immediate and tangible. This is because the scales we operate on are so small compared to the scales of the universe that the larger pattern is effectively invisible to us. But when we step back, when we consider the full extent of the cosmos, that pattern becomes unavoidable. Most of the universe contains almost nothing. And within that almost nothing, everything we know exists. There is a quiet elegance in that idea, because it suggests that complexity does not require abundance. It does not require a universe filled edge to edge with matter. Instead, it can arise in small pockets, in isolated regions where conditions happen to align in just the right way. Stars form where gas collapses. Planets form where dust gathers. Life emerges where environments are stable enough for long enough. Each of these processes is local, dependent on specific conditions, and surrounded by vast regions where those conditions are not met. In that sense, the universe is not uniformly creative. It is selective. Most places are quiet. Some places are not. And we happen to exist in one of those places. That does not make the emptiness less real, but it does change how we relate to it. It is no longer something distant or abstract. It is the context within which everything else happens. It is the space that allows stars to shine without interference, that allows galaxies to evolve without constant collision, that allows light to travel across billions of years to reach us. Without emptiness, the universe would be fundamentally different. It might be more crowded, more chaotic, perhaps even more violent. Or it might fail to form stable structures at all. The balance that allows for long-lived stars and complex systems depends, at least in part, on the vast separations between things. Distance creates stability. Space allows time. Emptiness makes persistence possible. And so, what initially appears as a lack begins to look more like a condition. Not something missing, but something required. This does not mean that emptiness has purpose in a human sense. The universe is not arranging itself with intention or direction. But it does mean that the properties of emptiness, its scale, its behavior, its relationship to matter and energy, are deeply woven into the way the cosmos unfolds. They are not incidental. They are fundamental. And when we consider that, the emotional tone of emptiness begins to shift. It is easy to think of an empty universe as cold, indifferent, even bleak. A place where isolation dominates and meaning is difficult to find. But that interpretation comes from projecting human expectations onto a system that does not operate according to those expectations. The universe is not trying to be full. It is not trying to be empty. It simply follows the laws that govern it. And those laws lead, naturally, to a cosmos where emptiness is the dominant state. Within that state, structure arises, evolves, and eventually fades. Not as an exception to the rules, but as a consequence of them. Which means that everything we see, every star, every galaxy, every moment of light, is part of a temporary arrangement within a much larger and more enduring emptiness. That may seem diminishing at first, but it can also be seen in another way, as something rare, something unlikely, something that exists not in spite of the emptiness, but because of it. And perhaps that is the most balanced way to understand it. The universe is not empty in a way that removes meaning, nor is it full in a way that guarantees it. It is structured in a way that allows for moments of complexity within vast stretches of simplicity. Moments like this one, where, within a small region of a large and mostly empty universe, something is able to look outward, to measure, to reflect, and to ask questions about the nature of everything that surrounds it. And in doing so, to briefly illuminate the emptiness that makes it all possible.